Thank you very much, Sonia. Thank you very much for the invitation. So I will tell you the story of this work. This work was motivated by a collaboration with the French company Thales, which is dealing with many things, but for this study, it was around drones. Okay, they want to have a confidence set for the trajectory of drones that is in real time to know exactly. Okay, as you know, there is control law and so on in order to pilot this drone, but at the same time, they want to have confidence region that is because generally the drones are not flying alone. They are flying. There are many drones at the same time, and so the problem in the control law is try to not crash the drone together. And so we begin this study trying to see how we can handle that. That is, and we begin to work on what is called conformal inference, and maybe you have heard about that. Conformal inference. I will explain the basic idea of conformal inference, but more or less is a technique that is or techniques in order to if you have something to forecast, okay, you have a model to forecast it. So of course, when you forecast something you don't know by a model, you make some error, okay. So and the conformal inference aims to learn the error, okay, learn on the error without modeling, completely without model, and try to for the next prediction to give some confidence set, okay. So it's very useful in what is the complicated forecast models that are used everywhere now, that is neural network, in which it's not possible to, it's difficult to understand what are the errors when you use a neural net. But what you can do is to try to learn the error and then to more or less extrapolate the error. Okay, the basic idea of conformal inference is very simple, okay? Is only imagine that you have exchangeable variables, or if you want, independent, identically distributed variables, okay? Okay, this, you have a training set of IID variables, and now you have a new realization, okay? So if you order the training set, because the variables are exchangeable, all the order of this variable could appear at the same probability, okay? That means that if when you are ordering random variables which are exchangeable, okay, each of these variables can appear at any configuration. More generally, if you are looking at the permutation that is ordering your sample, this permutation is uniformly distributed on the symmetric group. Okay, that is the main idea of conformal inference, to use this fact that is when you have something which is exchangeable, the distribution of the order is completely uniform. So what does it mean? That means that if you have a first sample with n realization, okay, you can forecast that the next realization will fall with high probability that you are fixing in some interval you learn with the data. Okay, is it clear? This is really the central idea of all this theory. That is, when you have exchangeable variable, if you have a first set, then you take a new one, and after that, okay, you can fix an interval with high probability, with bound that you will know, which are the observed given by the first sample, in which the new variable will fall with high probability. That is, with a small risk, you will be away from that. So the conformal inference is very popular, like this 5 or 10 years, since 10 years. There are many work in that, generalizing this idea. And what we have done here is we try to use a very simple regression model to learn the error. Okay, so that's the main idea. That's two main ideas in this work. Okay, the first idea of this distribution exchangeability, that is when you have an histogram of IID variable, if you take a new variable, you take the empirical histogram and you can fix the probability. With high probability you are fixing, the new variable will fall in an interval you know. Okay? First idea, and the second idea is we arrive to combine that with a very simple idea, is that when you observe errors, okay, I will be clearer after that. If you observe another exogenous variable, what is called another regressor, you may try with a very simple model to try to explain the error and to put information. This is the two main ideas. So this work has been done in this project with Thales, with two collaborators, which are Jan Anderson, which was a postdoc, and now professor at this school, Isaïe Supero, Adrien Mazoyer, which is in the same lab and Toulouse, and is assistant professor. Okay, so what more or less, what is the agenda of my presentation? I will be more precise because I try to explain by hand what is conformal inference. I will be more precise with some symbol, and then I will explain generally how it is done in regression problem. That is in regression problem in which your predictor is given by some regression model. Okay, then we will turn to the construction of the score, that is introducing some information by an external variables, okay, on the error. This will lead to all this theory, which is important. It is a non-asymptotic theory, okay? So we will see that we can build an ellipsoid, okay? That is, we can the region we want to forecast something which is vectorial. It will be an ellipsoid, and after that we will try to compare this ellipsoid to a more standard conformal prediction, in which you don't incorporate covariance. Okay, and I will present to end some numerical application on artificial data. Okay, so let's be more precise about conformal inference. So conformal inference, as I say, what you are observing is more or less you can think in IID variable. Okay, but this works for as soon as you have an exchangeable variable. So remember that exchangeable variable means that if I am looking at the distribution of this zeta, if I put any permutation on the index, the global law remains the same. Okay. So in case of IID is of course exchangeable. So you observe the n first variable, and what you want to build is some random interval, okay, based on the first part of the sample, such that with a high probability you are fixing the new variable will fall in this random set. Okay? Take care that here we are integrating, okay, there is a trap. Here we are integrating over everything. That is, we are integrating over all the variable up to Zn plus 1. Okay? Here, the interest of such a method is that I didn't make many assumptions. The only assumption we have made is exchangeability. Okay? This is the good thing. Okay, the bad thing is that in this generality, if you use this kind of method, they are very conservative. That means that the random interval will be quite big. Okay, this is normal. So just to mention that there is really actually a big interest in conformal inference, but this method is quite old. It was launched not in this context, but in reliability. It was a very old method launched by Wilkes in the 50s, okay, which is called, for people who make reliability, it's called the Wilkes method, which is exactly this idea, okay? Okay, so as we said, what is the generical method, how it works? Okay, for example, if you take, it will be clearer after that what is this score, but okay, you take something which is called a score, and what you are looking is the rank of the score, that is, you are ordering the score, okay, and okay, you have this score should be exchangeable and uniform. And so in order to construct the true region, you just have to do that. Okay, that is, you are taking just the good fraction of the rank you are dealing with. You are interested in with the good level alpha. Okay. Okay, is what I explain in the. Okay, I introduce. I pass from the Z to the score. That is, each time you are considering something. Here it's very simple. It's the absolute value. But each time you are considering an exchangeable function of the exchangeable variable, it will work. Okay, that is, you are reasoning on the score. Here the score is very simple, it's just the absolute value of the variable, but each time you are working with a score which remains exchangeable, what we say will be okay on the score. Okay, that is, you can locate with high probability the new score. Okay, so for example, here you have an interval which is okay for the absolute value will be 0, a, minus infinity. Okay, so generally, what score what are the score which are used? This is the most popular score is this absolute value in which you take for Z the observed error. Okay, that is, you have a model, you observe the true value of the model, you compute the error Z, you take the absolute value, and then that gives you information for the next error, for the next absolute value of the error. Okay, with high probability, you can forecast the next error you will make. So this is the one-dimensional case in which you take you take as the score, you take the difference. This zeta is just the difference between what you have observed, what you want to predict and the predictor, and you take the absolute value. Of course, an obvious generalization if you are forecasting not only one real variable but a vector, is to take the norm of the residue. Okay, you take the norm of the residue. Okay, and that will be okay. If you take, for example, p equal 2, that will give some square around the new point. Okay, you know that the new point, the error of the new point measured in terms of the Euclidean norm will be in a range. Okay, and so that will give you something which is a ball. Okay, it's clear. Okay, but as I mentioned in the introduction, okay, here I take scores. Here it's scores. Each score is depending only on one variable. As soon as we have scores which are depending in an exchangeable way, you can mix everybody. Okay, that is, you can imagine a score which is quite complicated and which is depending on all the n+1 variables. If the score remains exchangeable, all we said remains true, okay? By considering only the way this score will be ordered. And then you make exactly the same thing. Of course, it's much more complicated from that to when you will compute Sn+1 to extract the information on the new variable. It's completely intricated. Okay, that is okay. The theory, you can use the score you want. Even it's the only assumption you have to put is that the score remains exchangeable. But after that, you should in the inference for the new variable, the information will be complicated to retrieve. Okay. Okay. So in regression, what is the model in regression? So we have a quantity we want to forecast, and we have a covariable xi. Okay. You have a given, generally you have a predictor. This is given. Okay. This predictor is not built on this sample. The predictor has been built with another sample. Okay, you know that it is known. It is not depending on the sample. Okay, and what you assume is that you have that the new variable, the new one, is exchangeable. Okay, and okay, you have observed only the n first quantities. Okay, so given the n is what? Okay, you want to combine the conformal inference with the fact that you will observe the covariable at step n+1. Okay, so the aim is that to mix conformal and some kind of new regression model in which you will have your input will be this variable. Okay, so what we want, our goal is to achieve that. That is, you want to forecast the new variable by using that and using conformal inference. Okay, so the score function is the one I explained before. This is the classical one. This one leads to ball. Okay, and actually you don't use the new variable, right? You use your predictor, but you don't use the x part. Okay. In general, if you use that, in general, if you use this norm, you will have a very huge domain, okay? Because you only you are just only using the residual, and you are using the residual and the new value only in your regression, in your predictor. Okay, you will use your predictor only. Sorry, you will use your covariable only through your predictor. Okay, but you will not use all the structure that is the correlation of the x with the error. You use the error and the predictor that you have previously formatted. Okay. Okay, so I give you the reference and will recap the contribution, and after that I will explain the score we have used. Okay, so the paper is in this all link. Okay, so what we have done is that we have integrated in the conformal inference process the correlation in one sense, that is the connection between the error you are making and the covariable. Okay, that is, you fix your f hat, this is fixed, but the algorithm will more or less take into account the correlation you have, the connection you have between the error you are making, that is the difference between your f hat and your true value, and the covariable. That's the main idea. Okay? This is done in such a way that it's tractable. Because as I said, you can imagine, you can invent very complicated score, but after that, it's quite complicated. Because, why it's complicated? Because you will have an implicit equation to locate your new prediction, that is to give the trust region. It will be very complicated, and actually it will appear to be very tractable. Okay, and after all, we give a theoretical study that compare the classical method, okay, the classical conformal inference when you are using the norm, the L2 norm, and the introduction of this knowledge on that is the law between the regressor and the predictor. Okay, so what is the score? The score is quite intuitive. The score is just so the V, you see the V is this vector now. Okay, the V will be this vector. That is, you are putting the R is the error, the regression error, and X is your covariable. Okay, so the quantity that we use in order to build this confidence set will be this sample, the sample of the error, and the sample of jointly the sample of the covariable. Okay, you see what we have at hand, so it's clear. We have the covariable at the same time on the first n member of the sample. You also have observe the error you have done with your predictor. Okay, and what you want is that to predict the next one, predict the next error, to locate the next error that we will. Okay, so the intuition is to say, okay, it's quite, the intuition is quite easy to understand. Is okay, the good thing would have to normalize everyone. Okay, in one sense, it's when you do that, when you are doing this normalization, if you know mu, that is, if you know exactly the mean of this vector on this covariance matrix, it's a way to normalize the error. Okay, of course, the difficulty is that you don't know either mu nor the covariance structure. Okay, so what you have, what you do for this score, what you will say, you will do, it's quite intuitive, is just to estimate this quantity. Okay, you estimate this quantity, so the mean is it's quite easy to estimate it, and you estimate the covariance. Okay, you don't estimate exactly like that. You put some regularization in order that to be that's defined. The inversion is not so terrible. Okay, that is you are putting some regularization, but at the first glance, imagine that you are just estimating the covariance like that. Take care that as we want, that is the difficulty. It's a very simple quantity, but what you want to do is to have a score which is exchangeable. So you have to put everywhere the full sample. You don't know the new realization of R. Okay, you don't know that. But in your score, you have to put this R that appear to be a variable. Okay, it's here that you will have an implicit equation. It's because it depends on something you don't know, because it's the thing you want to forecast. But in order that the theory is working, you have to introduce in your estimate, in order that it remains exchangeable, the last variable. Okay? And after that, of course, what you are doing is that you take this intuitive score and you replace the mean and the covariance matrix by the estimate. Okay, so all of that is depending on the next that is the observation you don't have. And what's happened is that you can compute everything by the way of some interesting but classical show complement formula in order, because the main difficulty is in the inversion of the matrix. Okay, so using I will give some detail using this show inversion formula. You can show that actually with high probability, that is, you fix the error probability to be alpha, you can build something which is like that, which is an ellipsoid in your space. Okay, that is, you will more or less, this is a new center, that is, before you have this y hat, you can build a new center and a matrix which is here, in order that to locate with high probability this is the new observation. You can locate the new observation with high probability. Okay, so this will be an ellipsoid which will appear to be smaller than the naive sphere that I presented before. Okay, so what you more or less with and what you have done is exactly what you explain, is that you have correct in one sense. Okay, this is the initial prediction. This is the initial prediction. this is the initial prediction. What you are doing is that you are correcting the center by a regression term with respect to what you will observe, and here some noise that you are locating. Okay. And everything can be, of course, everything can be learned of the first part of the sample. Okay, this is no more implicit. That is, you really can compute all this quantity by the first part of the sample. Okay, so some detail. Here you have some detail on the computation. I don't want to enter too much in the computation, but the main thing is that here you can see here that it's terrible. Each time it's okay. Here more or less this is you can see something which is this show complement. Okay, more or less all this work because you manage to compute and to make some approximation in the inversion of the matrix using the show formula. Okay, so I will repeat exactly what I say is that more or less what you have done is you make a new regression. What you have done is very naive in one sense. It's just you have made the regression of the residual with respect to the variable x, okay? And you have combined everything in the machinery of conformal inference. Okay, now we can, what we have done is we have tried to locate more or less this ellipsoid in order to see if more or less this array was lesser or bigger than the naive, that is the classical residual, in which you only consider, for the score, you only consider one by one, you only consider the local residual between y and y hat in norm, okay? And what's up here is this, okay, I don't want to maybe to enter in the detail, but what's happened is that, okay, is that more or less asymptotically, when n goes to infinity, if you assume that your residual has elliptical distribution, then you can show that the volume of the trust region will be lesser than by the naive approach. Okay, it's asymptotic and under condition on the error, which is okay. It's an assumption that you cannot really verify. But if you assume that the error in your initial regression model is elliptic, you know that by this technique you will reduce the volume asymptotically. That is when your sample is going greater and greater. That you will be at least in terms of the volume better than the true the simple model, okay? So this rely on quite complicated computation on the quantile. That is, you have to compare asymptotically the quantile of the classical method with this method. This can be done. And just to maybe to end, I will just present some example, okay? And what is this example? We will have a look to to a pair of Gaussian vector, okay, Gaussian data, which are centered, we don't put mean, and which have a covariance which is classical, which is the Matern covariance, okay, which is given by this formula. So what we have the global vector will be lying in the space of dimension 9, okay. So what you see the picture is that you're observing this part, okay, and you want to predict this part, okay. Okay, and I just show you the case of the Gaussian data, which are here. So more or less, it is at the asymptotic, that is for a very large sample. Okay, for a very large sample, this is the green sphere. The green sphere is just the classical conformal inference. Okay, and the blue one is the one you are obtaining by the conformal method with the correction. Okay. Okay. This is exactly the same picture, but we just rotate the plane. Okay. That is here in this direction. It is inside for one direction. It is inside the. Okay. That is it is like that. Huh? Okay. For one direction, it is inside in the ball, and for the other, it is outside the ball. But what is interesting is that the volume, okay, for the volume of the ellipsoid is much more smaller than the volume of the sphere. Okay, at the asymptotic, because okay, you have so many points. At the asymptotic, it's okay, you have like a factor 10 in this model between the volume, and what you see is that, of course, you see here that the points are around this axis, and the technique learn it. The technique learn that okay, you have you have this axis as the axis of the point. And of course, the spherical model cannot learn it because you are not learning what is the distortion in your point. Okay. Okay, and so this concerns the way you are covering everything. Okay, so this is here we took. Alpha to be 10%. Okay, so here is the coverage in the previous model. That is only previously it was on. Okay, you have so many points. That is like an infinity of points, and now here you have only 200 points. Okay. That is, you have 200 points, and with the 200 points, you want to forecast the next one. Okay? So, of course, you want to estimate how is the coverture, that is the probability that indeed the ellipsoid you have built will contain the next point. Okay? You want to have the empirical probability because it is by simulation. So you have to make some runs in order to estimate a probability. You cannot estimate a probability just with one run. Okay, so you have to we take 500 times. 500 times. We use 200 points to predict the next one. Okay, it's clear. And of course, this will give you the probability to fall in the region which is built. Okay. just one number. If you want a distribution, you have to do that many times, many times. So we did that 10,000 times. Okay, 10,000 times. We predict 500 times on a sample of 200 variables. Okay, this is clear how we perform this simulation. So that gives you the distribution of more or less the distribution of the curvature. And it's more or less, you see that, okay, the target was, that this is for the ellipsoid in a previous model. The target was 0.9 here in red. And the mean of the observed is a little bit more. That is the mean curvature is better than expected, a little better than expected. Okay, and concerning the Gaussian sphere, it's exactly that is this small bias between what is expected and the true one is due to a fact that I have hidden in the computation, is that in order to compute everything, at what time you have neglected the term in the computation, which would have the good sign. So when you do that in all the computation, you introduce a bias which can recover here. That is, the method is pessimistic. That is, it works better that it is tailored to. Okay, and here are the volume. Okay, and what you see is that, okay, the volume for the ellipsoid is, as we have seen in the previous figure, is more or less you have a factor 10 between the two volumes, more or less. Okay, that is between the naive conformal inference, in which you take this score, which is only the norm, and this more complicated conformal inference, in which you make the regression, the linear regression of your error with respect to your covariable. Okay, more or less you have in this simulation you have a gain of 10, more or less. Okay, so we made also some many simulation in the case of distribution with high tail, because it's not forbidden. It's forbidden for the asymptotic analysis. In the asymptotic analysis, you have to assume many things in order to make the computation. Use the law of large number and so on. You have to need that the residual has the second moment. But actually, the method in this architecture, there is no assumption. Okay? And what's happened for the distribution with e-tail is that it works better. This is due to the fact, if you remember, there is an inversion at the time. And for actually the empirical covariance matrix is very big. When you invert it, it's very small. Okay, there is an effect. There is a normalization effect that make the method working very well for e-tail. The problem is that it's much more complicated to show things. That is, you don't have any more law of large number. So you have to already enter in the inversion, and it's quite difficult. Technically, it's very difficult. We also use this method in the case of multidimensional time series, in which you are cutting the sequences, okay, in which you don't have any more the assumption of exchangeability, because there is some causality. But experimentally, we have implemented that for Thales, and it works quite good. Okay, so maybe I will stop here. So thank you very much for your attention. So for me, the message is that really conformal inference is it's quite interesting, but the main issue in all of this theory is to try to construct a clever score. That is, really everything is in the score. And the main problem is that generally, if you have a score which is interesting, it's not tractable. There is there is something magic, that is you are mixing everybody through the estimation of your parameter, but you can develop the computation in order to extract the region, okay, the ellipsoid region. Thank you for your attention.